people that a lot of people expressed interest in, and about 45 minutes until dinner arrives. So the talks that a lot of people were interested in were scalability issues with Kirill, interactions with the VM subsystem, Brian, multi-tenant ZFS, Rob, and examining the on-disk format with Max. So what do people think? Should we like give each of these talks 15 minutes and just go a little bit over, or are there some of these talks that are more interesting than others?
Could we just go have them plow through, and when people start, gonging them off the stage, and maybe if we
everybody's too polite to do that.
if we have dinner,
by the timer.
yeah, I'll get my own done. And
Cutting eggs.
I have it downstairs. And if we start eating dinner while people are still presenting, that probably isn't the end of the world either.
All right.
Don me off the stage to disagree.
There you go. All right. So, Kirill, would you like to go first? Okay, so we'll do them in the order that I mentioned. So, Brian and whoever else is leading the discussion about interaction with VM subsystems, you'll be next.
Okay. All right. So I actually don't have a PowerPoint, and unfortunately, or fortunately, in the context of time, Adam covered a lot of the stuff I wanted to talk about, because at an example we had a lot of the same issues as at Behlendorf. So basically, yeah, we see several scalability things that come up with customers for a variety of reasons. Well, not the worst ones, but the most complicated ones are where customers decide to scale up way too high, or to the point where it doesn't make any sense, or to the point where
what are they scaling up? Like memory, number of disks,
anything,
size? Okay.
Anything. So we have deployments of up to 480 drives in a single Z pool, which may get into a pickle where you're just CPU bound, or you don't even have enough memory for metadata. So you're just stuck on I/O, or you're just not even utilizing your disks to any meaningful levels. You've got the customers that try to scale up SSD systems, all SSD pools, let's say just all mirrors, 60 solid-state drives in a pool, so 30 VDEVs. And you'll see that even on the fastest head nodes, like dual top-end Xeon E5s, they cannot push the SSDs more than maybe to 10-15% busy. So of course they're not very happy about it, because they've bought $500,000 worth of drives, and they get just several drives worth of performance out of them.
In those cases, on the SSD case, have you guys looked to see where your bottleneck tends to be?
Yes, we've profiled it, and so unfortunately I've been pulled away on some other stuff. I do have an in-house SSD system now where I can play with it. A lot of it is in locks. So, and it's both the RPMFU lock. I'm hopeful that some of the Delphix changes will help that.
It'll help. It's probably not going to totally solve the problem. It'll help.
So there's room for improvement for sure, and it's a lot of locking issues, a lot of things that unexpectedly start taking longer as your slow functions in the spinning disk context become really fast. So Metaslabs start playing more of an issue.
Is this also on like small block size?
It can be, yes. So it's most visible on small block size.
Because I think a lot of these locking issues are exacerbated, but are basically proportional to the number of blocks rather than the amount of storage. So small block systems tend to hit these locking issues.
So yes, it's exacerbated essentially by the amount of IOPS that you're pushing.
Yeah,
so
exactly.
The smaller the block, the worse it is in terms of the amount of work you have to do per megabyte.
Mm-hmm.
And in our testing on both OpenIndiana and on our current development branch of Nexenta Store, which is a few months behind, I was not able to push more than 130,000 write IOPS out of any pool, like not even a pool that's supposed to be able to push 1 million from a raw disk perspective. So this is where we stand kind of in a write performance scalability perspective, and it's especially sad because Windows storage spaces can push 600 test
Where's the bottleneck?
The bottleneck is in CPU, so it's exacerbated by the locking.
Which locks?
There's a variety of them. I can probably publish the data openly. I'm not really trying to hide it, but I don't remember. So there were ARC locks, some ZIO locks, some task queue stuff. Probably a lot of the stuff you've seen already.
Yeah, I think that's another way that the community, like, if it's, you know, obviously if it's customer data, maybe we don't want to necessarily publish it, but it would be good to like start having those conversations and those threads in the OpenZFS community as we look at them and can try to brainstorm on what, if it's a problem that's already been solved or it's something new that needs investigation.
Yes, absolutely. So one thing that's kind of beneficial about our customer partner model is that a lot of times we have partners that build those in-house systems that they test before shipping to the customer, and they come to us to see how we can tweak or optimize those systems. So the large SSD system, for example, was at a large partner that also happens to manufacture SSDs, and they gave me unrestricted access for like a month to play with it, but then unfortunately they had to take it away. So that's still an outstanding issue. Another area is ARC specifically. So regardless of what your disk backend is, and I'm not sure if that is going to be the same on other platforms, on FreeBSD and on Linux, so it might be specific to the memory allocator, KMEM. We are seeing that, first of all, there are those spurious reaps that end up deadlocking the system for seconds at a time, deadlocking it so bad that the network drivers cannot allocate memory for packets, which means that the box becomes not pingable, which means that the cluster heartbeats drop, which doesn't make everybody happy. So those reaps are visible, are very much more visible during a abrupt change in workload. So if we were, for example, pushing mostly a small working set size, and we are mostly in MFU, and suddenly a big backup job runs on some different data set, and those blocks that the backup job reads are still in the ghost list for MRU. So now we have MFU scaling down rapidly, MRU growing rapidly. And as far as I know, there's not a threshold or there's not a limiter that will actually slow down this rapid progression of going from one cache to another cache. Same really goes for different block size workloads. So when you have a mixed use system with, let's say, NFS shares at 128K, and you have some zvols at 4K, some zvols at 16K, something like that. Again, so as the system goes through its daily or weekly or whatever life cycle, you have, let's say it's a VDI system plus some files plus some databases. So in the morning, your users log in, they go to the 8K blocks, the cache is populated. In Solaris, ARC actually is, so the memory goes into buckets, into slabs that are of certain size blocks within them. So each slab is 128K, and it can contain smaller chunks that are equal within the block. So the way the memory scales up and down is it looks at each size that the system needs. Let's say we need more 4K, so it tries to reap all the other ones. But as you move between the workloads, you can end up again in a situation where you need to drop gigabytes or tens of gigabytes, or sometimes hundreds of gigabytes of, let's say, 4K buffers, which is a very very memory-intensive operation and a very CPU-intensive operation because of crosscalls. Again, this can cause a deadlock. Sometimes it actually does cause a complete deadlock. I believe Boris worked on a case like that where we got it to a point where it's not a complete deadlock. So it slows down, but it doesn't actually freeze the system completely, requiring kernel panic to get it out.
I recall a couple of scenarios that I probably will on.
Yeah, so there's quite a few. Also, a lot of those are difficult to troubleshoot because you don't know if your CPUs are used up by the reaps, or so you don't know where the root cause of your bottleneck is. For example, you may want to add more CPU because you think you're running out, but adding more CPU cores just means you have more crosscalls. So in effect, it might slow the system down. So you got to find a balance, and I do not have the answer to what the balance should be yet. Right now we're going by the mantra of fewer, faster cores.
So where do you see, like, there's a lot of problems there.
Yes.
Where should we or you focus your efforts in order to attack the highest value, lowest cost things there?
So right now, write performance and the memory instability are the two key areas where I think we should focus our efforts. Those are the top two things for an Exenta right now internally as well. So we're going to be doing a lot of work there. Hopefully, I hope we'll base it on your work to eliminate things that...
For the right stuff, at least.
Yes,
Yeah.
For the right stuff. But I am sure that once we optimize, or once we get those to be somewhat stable, there's going to be another challenge because, of course, the systems keep growing. 2 years ago, a system with 256 gigs was almost unheard of. Now we have customers deploying 512. And in some cases, I think somebody's talking about a terabyte of RAM.
Yeah. So I think
So it's a game of catch up.
Yeah, I think that's a pretty good transition into the next talk that we have planned, which was talking about the VM subsystem, right?
Yep.
And since you're saying a lot of these problems are with the
Yes.
not necessarily VM subsystem, but with memory allocation, and I think that's related to your stuff.
If I might just say a couple things.
Yeah, sure.
So there's one thing that Kirill's mentioned about ARC and the transition between different workloads. I've looked at the code, and it seems to me that the ARC eviction code is somewhat simplistic in that it chooses the fixed order of going through the list to evict stuff, like first remove them or you. And it would seem that if the workload changes, then we might want to pick a different list to start with, because that's the one that we actually want to throw out of everything, for instance. And I don't know how much it's going to help, because I haven't tried to prototype it. But the other thing is with the multi-model workloads. My look into it indicates that it's kind of leads to the virtual memory arena implementation, the arena implementation. And the classic case is like when you fill up, or almost fill up, all the ARC with small blocks, then randomly overwrite them, and then start filling up with progressively larger block size. Which seems like a pathological use case, but sometimes it happens. So you start with, let's say, fill it up with 8K, overwrite it randomly, and then start filling up with 18, 32, 64, and 128. And sometime at that point, the test implementation goes away pretty much.
I mean, I think creating test cases like that can reproduce these performance problems is going to be super valuable to actually fixing them. Because when you only see this on a customer system and it happens once a day,
Right.
like that's really hard to diagnose or to evaluate a fix. So
Yeah, and I've had systems where it happens once a week. And so that particular one, it was attributed to a Microsoft SQL backup job, which was the precise change in workload that induced it without fail every single weekend, sending the customer box offline for 30 seconds or so.
Do you have a comparable workspace or test case that doesn't require like SQL Server to do it?
Yes, we do have test cases that are synthetic, essentially just VD-bench scripts that try to simulate this. But the biggest problem with this sort of test cases is they really require a very large test system to be visible enough to show that it's a real problem. So in my case, the biggest one I have is 288 gigs of RAM, and it's sufficient for this sort of stuff. It will not be sufficient once we have eliminated the low-hanging fruit, I'm afraid. But that's something I'm talking about with the guys at Nexenta, so hopefully we'll be able to scale with our customer base there.
Thanks, Kirill. And
Well, I don't have slides either, so I'll try to keep it quick.
But I'm actually encouraged to hear that other people are looking at the memory management stuff too. I had feared for a while that this was only something I was going to afflict the Linux port. But knowing that there's works on the other platforms is actually a little bit encouraging to me, believe it or not. So the problem we're suffering with on the Linux port, I'd say probably our biggest stability concern at the moment is the memory management. And it's a problem because we basically took it over, kept it unchanged from FreeBSD and was as best as we could. And the problem with that is Linux's memory management subsystems work very, very different than FreeBSD and Linux. Certain things that you would think would be fine just aren't the way you do it in the Linux kernel. So case in point, large memory allocations. All right, so anything over, I would say, a couple of pages in Linux, pretty much you should think about allocating pages for them if you want to do it fast. We have Kmalloc and we have Vmalloc, but the situation in Linux is Kmalloc is fast for a couple of pages, and Vmalloc is strongly frowned upon, that you should not use it. It is not a good interface. It is not a fast interface. It is not meant to be a fast interface. It should not be relied upon. So early on in the Linux port, knowing this, we decided that because we didn't want to go through all of the ZFS code when it wasn't working yet on Linux and fix up all the code to do scatter-gather based page allocations, what we do is we put a layer in our SPL to try and make Vmalloc work reasonably well on Linux. So what we did is we implemented our own, basically Femaleic back slab in Linux to try and make that behave pretty well. So we wouldn't have to change any of the ZFS code, it could stay unchanged, we could get it working. That's worked pretty well, actually, for a couple of years now on Linux, but it is clearly one of the creakier parts in the current implementation. The thing that needs to be fixed probably soonest. It got us a long ways, but at the end of the day, we just can't really get away with doing large memory allocations in the kernel on Linux. So to address that, we've been thinking about how to replumb ZFS to use scatter-gather lists for all the large ZIO buffers currently that come off of a slab. That's one thing I wanted to talk to this group about in particular, is if we're going to go down this road, what's the best way to rework those interfaces in a way that's workable for everybody? Should we just put wrappers around them so that you guys can continue to use Femaleic and be free in the current Slab implementations? And we can do something more Linux specific? Or is this a bigger problem for everybody else going forward that maybe we should all move towards a scatter-gather sort of infrastructure for ZFS in general? And I think that's still, we know we have to do it for Linux, but I'm curious how much of a problem it really is for the other implementations.
Can you kind of describe, maybe I missed or didn't quite understand, like what is the exact problem? Is it like you cannot allocate contiguous virtual address space?
No, so the problem, I guess there's a couple problems with Linux. That's worth explaining, because I think most of us aren't Linux folks here. Yeah. So you can absolutely do it on Linux, but you have to be aware that it's a global address space in the kernel, and it's covered by a single lock. So if you do a Vmalloc, you take a global spin lock on the system. So everything gets serialized through that lock. So it's not that it doesn't work, it's just that it's very, very slow to do. So it's frowned upon. Improvements have gone to the Linux kernel for the last couple of years to speed that up,
But fundamentally, it's all still serialized through a global lock, so it's expensive.
And are you using like a slab allocator so that you aren't going to that global lock for every allocation, only when you need to get into slab?
That's what we did in the SPL. That's the slab allocator we wrote. We said, okay, well, we know this is what Linux is going to do. We'll allocate pretty big slabs, and then we'll just carve them up internally, right, and avoid getting that global lock. So that was the dodge we pulled to get around this being a really bad problem.
And for Linux, you're doing that for anything, any allocations greater than 8K?
So
4K?
basically, there's two types of allocation. There's Vmalloc and there's Kmalloc. So if you do anything that goes through Vmalloc goes through that global lock. It'll be serialized. Anything that goes through Kmalloc is quite fast and is backed by a slab, but there's a size limit on it, right? You probably shouldn't allocate more than, I would say, 2 pages, probably. So 8K.
Why is it that you don't want to allocate more than 2 pages?
Well, there's a good chance of it's failing, because if you go through Kmalloc on Linux, it has to be physically contiguous in memory. So you're looking for physically contiguous pages at that point.
So and your kind of current workaround is to use Bmax and allocate a large, kind of create your own slab that you carve up, and
Exactly.
that handles anything greater than 8K
Yes.
today? So
Yes.
8K to 128K, you kind of do your own management of it?
Yes, exactly. Linux does provide its own slab, but it's got these restrictions, right? Like, I think the biggest thing you can actually allocate out of the Linux slab is 128K. And don't count on it being fast, and don't count on it succeeding, because it's totally possible for it to fail and say, no, you can't have one. That's a totally legitimate way for the allocator to behave.
Can you describe what you mean by scatter gather and how that's going to help?
Yes, so I was getting there. So the solution we're proposing on Linux is basically for file systems, all the file systems in Linux don't do large memory allocations, right? They allocate individual pages. They get individual pages from user space for I/O that's going on, and they feed individual pages to the block I/O, block layer, right? And they assemble those into just scatter gather lists as they get passed through. So it's a set of pages, right? Just a list of pointers, and so these pages, they don't need to be physically contiguous in memory, right? This is my I/O, this is my buffer, and then it's
Or virtually contiguous, for that matter.
right. They are not even mapped into the address space. So that's why it's better on Linux. You have these set of pages, and they have physical addresses, but they have no virtual address.
But I mean, they need to be mapped in, like, to checksum of them.
Yes.
Is that going to destroy performance?
So that's an open question. So
Because like normally, like creating a mapping, you have to go shoot down the CLB with all the other CPUs, and that's like changing the address space is usually not very fast.
But
Right,
in this
so-
case, it can be done one CPU at a time. So on i36, you can do a local temporary mapping on a page-by-page basis without shooting down all the other CPUs.
Right.
On AMD64, there's enough address space, you can do the direct map. I'm guessing Linux has a direct map as well, so there's frequency, and so there's really almost no cost
And you ping
Right.
your thread to that CPU?
during the checksum calculation. Absolutely.
in fact, you have to on Linux. So you take the buffers and you map them to that CPU for the operation you need to perform. There's certain restrictions like no locking, right? You get spin locks, but don't ever yield the CPU. Make sure you unmap it before you're done.
Are you also like running at high IPL so that you can't take an interrupt?
Yeah.
Yes. In fact, all of that gets disabled. It is.
That's exciting.
it makes the programming a little more difficult, but it's really good for speed at the end of the day.
And the thread does not move across the...
No, they'll pin it.
That's why you're saying on shoot down the other...
Yeah. So you just map it locally for that CPU, and you disable interrupts, and
I'm surprised they don't just disable interrupts. I mean, on FreeBSD we would just pin it, and then when it returns, based on priority, you get resumed on the same CPU.
It's the way it works on Linux. So that would be, we would be looking at introducing wrappers to do that kind of thing, right? So instead of doing what now is allocating a ZIO buffer with Vmalloc, right? We allocate, maybe there can still be a wrapper that looks like that's what happens, right? Except you get this zbuff back, right? That you can pass around as if it were your buffer. Then on Linux, what you would do instead would be you would allocate a bunch of pages randomly from, well, not randomly, right? You just ask for a bunch of pages and you get them somewhere in the address space. And then you would have some wrapper functions to copy data into them or copy data out of them, to make a checksum, that kind of thing. but you would never need to map those pages into the virtual address space. Maybe we would have some functions to do it for operations that were harder, like maybe there's some transforms in the pipeline that would be really hard to implement on a page-by-page basis, or if they have
Like compression?
well, I mean, you can, like we were saying, as long as you don't actually need to yield the CPU, something like compression you don't need to, you can map it onto that CPU, and do the compression, and then you're good. If you need to do something else like, oh, I don't know, something where you have to take a mutex or something
So
like that.
are you proposing doing this for only user data?
I think as a first step, yes. We were proposing doing this just for the ZIO
I was doing that
buffers.
as a last step as well. Because, I mean, that would be extremely either disruptive or performance killing to do this for like all of the metadata, you know, because you're modifying it and reading it, you're reading and writing it everywhere. You know, there's probably like 1,000 places in the code where it's like, you know, update an indirect block, or update a Z node, or update a D node, or update a DSL data set,
Yes.
BizT, like
Yes.
all those things are mostly on pretty small blocks, but you know, the access to them is much less constrained than user data.
Yes. It's for that exact reason that we went through the hoops we did initially to make our own Slab implementation that was faster. We wanted to avoid all of that. But long term, I don't see how we avoid it on the Linux side. Or we can't really continue to do what we're doing. We need to do something that doesn't require us to map anything into the virtual address space.
Can you just like, when the system boots up, map all physical pages into the address space and then put an allocator on top of that?
Yeah, that's actually.
And not let anybody else use it?
That's not considered very friendly, but I suppose we could, yeah.
Yeah, we reserve a range of memory for what we call the KPM segment. Which is basically all virtual memory, all physical memories mapped into a region of VA on 64-bit.
Yeah.
I don't think we use that.
Yes, that's probably not practical.
It would.
You can do that on any 64-bit desktop.
Right, but then you don't use half the math. Right?
No,
Right.
that's not. Sorry, that mapping. Just because that mapping exists doesn't mean it's backed by DRAM all the time.
Oh, so it can be used by something else.
But it's just a region of VA that's mapped, not a region of VA that's used.
Have the needs of the port on
It's not faulted.
Linux been brought up to the Linux maintainers?
Yes, repeatedly. And they say, don't use Bmax. You should not use it, it's slow.
Well, I don't say we're using Bmax. Say, can you give us an allocator that works? Yeah.
Well, this is, so you got to remember
I mean,
this.
Solaris has had the slide allocator for quite some time.
Well, in Solaris it's the same problem, except it's alleviated with quantum caches, right, on the arena level. They also have a single walk female arena, and the way they make it work on multiple CPUs is that they have quantum caches for like so many sides of the computer. But the other thing is that all the caches are built on top of arenas, right? And arenas are sort of hierarchical, so that's how it all works.
Well, I think that you're. I don't have anything fundamental problems with like doing that. So, you know, I think there's a lot of ideas on how maybe like sure Linux should be better, but I think working within what you've got and doing that, you know, that's fine. And I don't think it's going to hurt. It's not going to kill anybody else. I don't think. So.
I should also mention that, we have brought it up with the, sorry,
We did read that.
with the upstream maintainers, and this is just more a philosophy thing, I would say, on Linux. This is not viewed as a bad thing. It's this, if you want good performance, you should not go through the virtual address space. It's just kind of baked into the culture. If they don't believe they're doing anything wrong, and I tend to agree with them, actually. Allowing this sort of thing is a convenience for the developers, right? And so I don't think we're going to be changing opinions there. So at the end of the day, we need to do something that just works.
Well, does it make sense to look at something at the portability layer and do it? Or, well, I mean, it's probably to
Yeah, it needs to be baked more into Zcash. You can't just do this in the portability layer strictly.
No.
So,
I mean, even the fact that we've tried to hide it, but there's other issues that come up on Linux. Things like you can't do any kind of sleeping allocation or Bmax in any write path, right? That will deadlock. shall not be done, right? So
Let's maybe say that for another.
so there's lots of this is a long
thread
thread to pull. It's the root of a lot of our problems, right? So we want to do something about it, and that's good. So if I got a few more minutes, I guess one other thing this lets us do on Linux at least is better page cache integration. We'd like to bring ZFS into the page cache on Linux. And if we start doing things on a page basis, we can actually do that. We don't have this problem of mapping these random buffers that are in a slab somewhere into the page cache. We can now properly map pages in, fault them in, and get rid of the ugly mmap hack probably that we have at the moment where we keep 2 copies of this. So I think it's a lot of work, but I think for everybody there would be a lot of benefits that would fall out of it. I don't expect it to be a quick change, the big disruptive change. I kind of hope to spend the next year kind of poking at it and moving it forward. So I don't want to underestimate the amount of work, but cool. So, thanks.
Should we do one more talk and then 5:30 dinner? Or is it getting? Is there? Okay. So dinner is here and getting cold. So let's go ahead and grab dinner. Come back here.
No beer until you listen to 2 more talks.
Yes, 2 more talks.
Get your dinner, sit down, no chatting.
Yeah, I mean, I think.
I'm surprised.
It's all good. It's fine.